Hello. So in this tutorial, I'll be showing you how you can generate some wavy patterns in Houdini. It will be a slightly Vex oriented tutorial. So if you know a thing or two in Vex, this shouldn't be a problem to follow along. But I'll be sure to cover through the basics. And after this, we'll be exporting to Cinema 4D and I'll be showing you how you can set up the render. So let's get started. Alright, so before we get started, I just want to explain a few things in brief. So for this thing to work, we need at least two meshes. So for the base mesh, I'll be importing a flat grid, a high density flat grid, so that we can get high resolution waves later on. And for the secondary geometry, I'll be using a simple cube for now as a placeholder. So the simple idea behind this is we need to calculate the distance between the grid and the closest point to the box to generate the waves. So the simplest way to find the closest point from the box to the grid is by using a Vex function called nearPoint. And what we can do with them is we can just later swap them out with the point positions of those points. So using these two sets of point positions, that is the point positions of the grid itself and the newly transferred closest point position, we can generate a distance between these two sets of point positions. So by doing this, there will be a value being stored on each point of the grid, which tells us how far away it is from the closest point on the box. So we can visualize this by changing it into a gradient. And by using this gradient, we can feed it through a sine function. So that will generate the waves. And what we can do later is that we can isolate these parts by color or by value. And we can convert them to splines and smooth it out. So that's the basic idea behind this. Now I'll explain further once we start doing this. So let's get started. Alright, so now that we are in Houdini, let's go type in geo and we'll dive in. And inside the geometry node, let's add in our base mesh, that is the grid. And we'll add in our secondary mesh, that is a box for now at least. So this is going to be a placeholder for now. We'll swap it out later with something else. So this is just for the simplicity of explanation that I'm using this. So on the grid, let's leave the row and the column to 20 by 20. Now at the end of this tutorial, I'll be increasing it to something like let's say 1000 to get those high resolution or a smoother wave. And in the box, let's change this to polygonal mesh, and I'll change the uniform scale to 2 for now, and I'll just reduce the axis divisions to the minimum. Now you can use something more complex like a pig geometry head or something like that. But the issue that I found is when you want to animate the waves on a complex mesh like this, sometimes it can get a bit unstable. But if you're going for a still frame or anything of that sorts, using this type of geometry would be perfectly fine. Anyway, in the next step, we'll code some things in Vex. Alright, so I'll divide the Vex part into a couple of different steps so that we don't overwhelm ourselves with a bunch of code and it's easier for you guys to understand. Anyway, let's dive in. So we'll add in an attribute triangle and I'll connect the grid to the first input and the box to the second input, like so. So basically the first thing that we want to do is we want to find the closest point on the box to the grid. So to do that, there's a simple Vex function called nearPoints. So let's go ahead and initialize a variable so that we can store the near points. So I'll name it as near. So it's an integer variable, and let's store the near point. And as you can see, there are two variants of it. So I'll be using the first variant and the second variant, which ends with a S, near points. It basically stores an array of all the near points. So in our case, we don't need that. So let me go ahead, type in open bracket and close it. And we'll add in a semicolon to end the command. So inside this bracket, we need to specify a couple of things. So the first thing we want to specify is the geometry to read from. And the second thing we want to specify is the geometry to read to. So the first thing is we want to obviously read the points from the box. So I'll type in 1. So right now the box is connected to the first input. So since we want to find the closest point to the grid, we need to specify the point position of the grid. So to do that, it's simple. We just type in @p. Alright, so let's try and visualize what's happening right now. So I'll convert the variable into an attribute. So for that, it's pretty simple. I'll just type in I at, let's say viz is the name of the attribute, equals @near. So I basically represents integer, and this is the name of the attribute. So let's go ahead and add in a visualize node, and we'll connect that like so. And let's go into the visualizer tab, and we'll change the type to marker, and let's type the name viz into the attribute name. All right, so now you can see there are some numbers being displayed. I don't know if you can see that, but let me enlarge on it. All right, so you can see a peculiar pattern going on. So on the top left quadrant, we have ones, and on the top right, we have fours. On the bottom right, we have fives, and over here we have zeros. So that's directly representing the point number of the box. So let me just visualize the point numbers on the box as well. All right, so you can see that right now it's picking up 1, 4, 5, and 0. So Houdini thinks that the lower part of the box over here is the closest to the grid. Let me just highlight the grid. Now if I move this box a bit to the, let's say, upwards or maybe down like so. So right now we can clearly tell that 3, 2, and 7, 6 are closer to the grid than the bottom points. So obviously it should reflect in the grid. So right now you can see that the numbers have changed to 3, 6, 2, and 7, which is the same as the top portion of the box. Now the numbers change depending on whichever it finds the closest to the box. So let's try and rotate the box in some weird way. So you can see the numbers change. So this line of code basically finds whatever point is closest to the grid, and it assigns the point number of that point to the grid. Let's import the point positions of these points onto the grid so that we can calculate the distance. So to do that, we need to initialize another variable. So this time it's going to be a vector, since we want to store a 3-dimensional position value. So let's name it pos. And we want to import the point attributes from the box. So let's type in point. So this is going to be basically reading the point attributes of the box. And we specify the input number. So that's going to be 1, because the box is right now connected to the first input. And we want to specify p, that's for position. So we give that in quotations. We only want to import the position of the point number that is equal to near, right? So if I just change this visualization to v, because now it's a vector, I want to visualize this position as an attribute. So I'll change this to v from an integer number, and instead of near, I'll now type in pos. All right, so now we have a position value being stored on the grid. So it's it's right now here it's 1 comma, I think 0.8 comma 1. So let's see if that's the same as is on the box. Yeah, it is the same. So it's on the box, it says 1 comma 0.8 comma 1. So that basically means the position has been transferred to the grid. So let me just change the type to color, and we'll, in the attribute name, we can type in what is it? I think it was yeah, we can type in viz. So viz for visualization. All right, so now we can't see much what's happening other than multicolored quadrants. So over here in the near points, we can also limit the search radius of the closest point. So we can give another comma and specify the search radius limit. So let's say 2. Yeah. So what it's going to do, it's only going to be searching the closest point from the box to the grid within a 2-unit radius. So now we have 2 sets of points. That is the original point position of the geometry of the grid. And the second set of point positions are the ones that we have transferred from the box to the grid using the near points function. All right, so to generate the distance, it's pretty simple. Let's initialize a variable using a float. So we'll call this dist for distance. And the function for calculating it's called distance, and it's pretty straightforward. We need to specify the 2 sets of point positions. So the first set is going to be at p, that is the original point positions of the grid. And the second set of point positions are the ones that we calculated from the near points. So it's going to be pause. So once we do that, we can't see much what's happening. So let me just export this variable as an attribute. So let's change the viz over here from vector to float, because we want to export this as a float. And instead of pause this time, let's type in dist. All right. So okay, it's being represented as a text right now. So let's change that to color, and right away we can see there is a kind of a gradient being generated. If I change the type to ramped attribute, we can fine tune the color. Let me change that to black. And the resolution depends on the divisions on the grid that you give. So let me type in 800 by 800 for now. So you can see clearly that we have a gradient going on. Now we can also control the search radius over here, and that's going to be affecting the gradient. So I'll be initializing another attribute, a variable. So this time it's also going to be a float, and let's call it wave equals to sine, comma, bracket distance, or dist actually. Okay, let me just reduce the division back to, like, let's say 100 this time. Okay, and we'll export this, and we'll call it wave. Okay, so right now you can see it's pretty huge. So what the sine function did is that whatever value that the distance generated, let me actually visualize that. Okay, it's can't read because the divisions are too much. Let me reduce it to 10 by 10. So this is the distance value that we have generated using the distance function. So what the sine function is going to do is going to take these values into consideration, and it's going to be oscillating them between -1 and 1. So by oscillating those values, we get kind of a wave pattern. So let me increase this back to 100, and I'll export this back as wave and change it to color. Okay, so obviously we need to control the amount of rings and offset them. So we can control the amount of rings that we have by multiplying the distance by a certain amount. So let's say 20. And we can also, so let me just, instead of typing 20 here, let's generate a float slider. So for that, let's type in chf bracket open, and in the quotations, let's type in rings. Okay, and if you click this button, it will generate a slider. So based on the slider, you can now generate rings. And if you want to offset them, you just have to negate it by some value. So let's say 5 minus distance. That's going to be giving us different kind of offset. So I will also convert this into a slider by typing in chf bracket open, in the quotations, let's say offset. So let's click on that button to generate a slider. So now you can see that it's being offset. So now we have a control for offset and a control for generating the amount of rings. Alright, so the majority of the things have been done. Now it's just the matter of fine tuning some stuff. And right now I want to make a controller so that I can make the lines thicker. For example, the black lines. Let's say I want to make them thicker. So for that, let's go ahead and initialize another float variable. So let's call this correct for corrections. And inside this correct, I'll be making a ramp so that we can control the thickness. So to do that, let's go ahead and type in ch ramp to make a ramp node. And you need to type the name that you want your ramp node to be. So in this case, I'll type in wave. And you want to specify the source. So I want to affect the wave over here that generates the rings. So let's go ahead and type that. So it will be affecting the wave. And that should be it. Let's go ahead and click this button. So in the attribute viz, let's now type in correct so that we can see what's happening. So something changed. Now you can definitely see something's happening, and we can obviously control the thickness of the lines, but it's very distorted in a way, and it's not looking quite right. That's because the sine function generates values between -1 and 1. And this ramp function by default works in the 0 to 1 space. So to fix that, we can, in the wave variable over here, what we can do is we can add in a fit function. So fit 0 1 is going to clamp our values between 0 and 1. So now it's looking pretty fine. Now we can obviously control the thickness. I mean, if you add more density to the grid, you can see that it works perfectly fine. All right, so let's go ahead and now isolate or delete the parts that we don't want. For example, let's say we don't want the black parts, so we can go ahead and delete them so that we can get nice looking rings. So first of all, actually, let me go ahead and press Alt E over this box while my mouse is over this box, and we can get the separate window. All right, so let me first visualize this. So I'll just change the type to marker, and right now we can't see anything. I think it's a bug, so you have to. Yep. Okay. So right now we can see that whichever area was black, it stores a value of 0 from the correct variable over here. And so we want to delete whatever is 0. So to do that, let's go ahead and type in this condition. So let's say if correct greater than 0, or let's say equal to 0, we'll put an open curly bracket, and inside this curly bracket, let's type in this function remove point. So this function is going to remove any points that fits this condition. And let's say remove point from the 0 input, that is our grid, at ptnum, so whichever point number, and close curly bracket. So let's click apply and accept. So now you can see that whichever parts were 0, they have been deleted and no more there. So let me just yeah. So this is looking pretty fine, but let's say you are in a situation where you want the edges to only exist, and anything in between you want them to be deleted. So let's initialize another variable. Actually, in fact, I'll be just copying and pasting the same exact variable over here that we use to control the thickness of the rings. And what we can do is we can just rename this to, let's say, edge. Okay, and let's leave this at default for now. Should be fine. Press accept and click on this button again, because it's a ch ramp, and it's going to be generating another one of those ramps for us. Oh yeah, my bad. We need to change the name of the ch ramp. So we already have wave taken by this ramp over here. So let's change this to, let's say, edge, and on that. Yep. So we have a new ramp with the name edge over here. So with this, what we can do is, let me actually just export this as a attribute, so that we can see what's happening. And let's go into the visualize, change this to color. All right, so it's still red from the previous rings. But what we can do now is that using this new ramp that we have generated, the edge ramp, we can invert this actually. What we can do now is we can go back into the attribute triangle. I'll press Alt E to open up that box, and we can copy the same exact conditional statement that we used to remove the black edges in the previous step. So I'll just copy that. I'll paste this again, but this time, instead of checking if the correct is 0, let's check this time if the edge is 0. Yeah, if it is 0, remove those points. Click accept, and now you can see we only have those edges. So now it's looking pretty fine. Alright, so I've just swapped out the grid with the picket over here, and I've added a subdivide node so that we can divide it further and get a higher quality mesh. So I fed that into the attribute triangle, and we get this sort of a pattern. Now, as I said before, sometimes it's quite unstable when you put the patterns on a complex geometry like a picket. But in this case, I'm pretty happy with the result, and it seems to be working perfectly fine. So we need to fine tune a couple of things. So first of all, we can see that we have a lot of small little pieces here and there, and they look pretty ugly. So let's go ahead and get rid of them. So how do we get rid of these small pieces? So first of all, we need to define what a piece is. Right now, Houdini reads the whole geometry as one object. So we want to separate these islands of patches of geometry into their own pieces. So we can do that by using a connectivity node, and we can connect that to the input. And in the connectivity over here, right now the piece name is set to class. We can leave it at default for now, and let's change the connectivity type to primitive so that it connects it connects each primitive. And we can visualize that better using a visualize node. And let me connect that to the input. And I'll change this to color, and the attribute, let's change it to random from attribute, and let's type the name class. So you can see that each piece has their own color. And let's go ahead and now add in a measure node so that we can measure the perimeter. Just extend this, and right now it's set to area. Let's switch that to perimeter. And right now the mode is set to per element. I think what it does is it calculates the perimeter of each polygon. But let's change that to per piece. So the piece attribute is the class. That's the same as we have over here in the connectivity. Now if your name is different, you can go ahead and type the same name over here. And let's change the output name to something shorter like peri, so it's easier to deal with. Now we can also visualize this. So let me go ahead and add in a visualize node. And in the visualizer, let's go ahead and change. Okay, it's set to color, and let's change it to ramped attribute, and we'll type in peri. Alright, so you can see that whichever is red has the highest perimeter value, and whichever has the the blue color, it has the least. Actually, let me just go into the geometry spreadsheet again, and we can see what the perimeter values are. So it ranges from 0 to all the way till 58. So the highest value is 58, probably this one, which is red in color. So anyway, let's go ahead and add an attribute triangle so that we can delete the pieces by perimeter. Now make sure the attribute triangle is set to run over points, primitives. So now let's go ahead and type in a conditional statement. So let's type in if bracket at peri less than 5, close that and open a curly bracket. And in this statement we'll write, in this conditional section we'll write remove prim. So we already typed something similar to this previously, but that was remove point. But in this case, since we are running over primitives, we want to use remove prim. We need to specify a couple of things. So the input geometry is 0, and we want to type in the primitive numbers. So at prim now specifies that, and we want to specify the point number, that is the pt num. So that should be done. And oops, sorry, I forgot to close the curly bracket. Alright, so now you can see that all the pieces which have the perimeter less than 5 got deleted. And instead of having the number over here, let's make a slider. Let's make a slider. So I'll type in chf open bracket, and in the quotation let's type in threshold as our name, and I'll close the bracket. And let's click on this button, and now you can use the slider to delete the small pieces. Alright, so let's go ahead and convert these polygons into curves. So to do that, we have this node called convert line, and it's pretty straightforward. You just connect the input, and it automatically generates curves from the polygons. And we can uncheck this for now because we don't need that. And what I like to do is I like to add in a smooth node so that we can get a more organic looking shape. And I like to reduce the filter quality to 1 and increase the strength to 50. And just for better visualization, let me increase the depth to 3 and just increase the ring amount. So before exporting, I just forgot to mention one little thing. So we can also calculate the color depending on the distance from the box to the pig head over here. So let me just move this box 5 units to the right. And let's go into the attribute triangle, and over here we can calculate the distance to generate the colors. So we can use the same expression that we used in the beginning to generate those rings using the distance function. So let's go ahead and initialize a new variable. Let's call it col, and it will be a float value, and we'll calculate the distance inside. And we want to mention the position of the points on the pig head, and the nearest point, that is over here, that we already calculated using the near points. And let's export this variable now as an attribute. So I'll initialize a vector attribute and call it col, and I'll store in the col variable. Now we can add in a color node and I'll connect that back to the network, and inside this color over here we can change the type to ramp from attribute, and let's type in the attribute color. So you can see that we can generate colors using this ramp node. You can also play around with the range over here so that we can get more of a coverage on our color. Alright, so there is two ways of exporting this. Let me just go ahead and add an ROP Olympic node so that we can export this as an animation. And let me set up the offset so that it changes on each frame. So for that I'll give the expression $F, and if I just let that run, so you can see that it's animating over each frame. Now we can control the speed of that by multiplying with a lower number like 0.4. Okay, let's leave it like that, and I'll just increase the subdivision back to 3. Now the first way we can export it is through this curve. So we can directly plug that into the ROP Alembic node, and we can change this to render frame range and delete the channel so that we can specify the frame end. So I'll type in 30, and to export it, let's click on that icon and specify a folder location. So let me type in polywire.abc to export it as an Alembic file, and I can click save to disk. And the second way we can export is by using a polywire. So let me go ahead and plug that into the polywire, and let me just instantly reduce this to 0.02, and we'll plug that into the Alembic, and let's see how that looks like. Okay, now I'll export this. So I'll type in meshed polywire, and I'll save to disk. Okay, so now that we are in Cinema 4D, I've just imported both of these meshes. So the polywire variant contains a couple of tags. So one of them is a vertex tag that contains the color data. But on this spline variant, which we exported without any polywire, just using a convert line node, we only have just the geometry. We don't have any color data. So this is one of the limitations of importing as a spline to Cinema 4D, that it doesn't store any color data. Now I'll show you how we can render both of these variants. So to render the spline version, I'll be using Redshift, but it should work in any other render engine. So to render a spline, right now if I just enable the render view, we don't see anything because by default renderers can't render splines. So to render a spline in Redshift, we can add in a Redshift object tag, and over here we have a curve section. So we can render this as hair strands. So right now we can immediately see that we get hairs being represented as our splines. I can also obviously control the hair thickness and the fall off. So let me leave that at 1. So that's how you basically render splines. And if you want to render polywire, you don't have to do anything special. We just have to enable that, and it will take some time to refresh and update the render view. So now we can see that we have the polywire version. Now if you want to use the color attribute inside the shader, let's go ahead and do that. So I'll add in a material and I'll apply it to the polywire, and inside the shader network, let's dive in, and we can add in a vertex attribute node. And what I can do is I can drag and drop the vertex tag into the attribute name, and if I just plug that into the diffuse color of the shader, and let me go ahead and enable the renderer. So that's the color getting picked up by the shader. Now we can also control the color using a ramp node. So let me go ahead and stop the render again, and let's this time add in a ramp node. And also we need to convert this vector, the vertex attribute, into a scalar. Right now it's imported as a vector because we exported it as a color attribute, and the ramp only reads between the values 0 to 1, and it's a scalar value. So to do that, we have a simple node over here called vector to scalars. So let's put that into the input, and we can just output the scalar into the ramp and connect that to the output. And over here in the ramp, let's set the source to alt, and with this we can control the color basically. Alright, so that's pretty much it. I hope you found the tutorial helpful. You can get the Houdini Digital Asset version of this as well as the scene file on my Patreon page as well as on my Gumroad. Thank you to all my patrons for the support. Become a patron today and you'll get access to all the scene files and the HDs I've uploaded so far. So that's pretty much it. If you have any doubts, you can comment them down below in the comment section. I'll try answering them. So that's been it, and I'll see you in the next tutorial. Take care.